want to welcome you guys all to James Noraky's defense. So James received his bachelor's degree and MN's degree at MIT in 2013 and 14. And his research, as you can tell from the title, kind of revolves around the design of low power systems for depth estimation. What differentiates it from other works is that while prior works really focus on, relying purely on the depth sensor, which could be very high sensing power, and then, or purely on images, which require high computing power. James is looking at the technique of developing methods to blend these two approaches so they can achieve overall lower power without sacrificing quality and latency. And he'll also showcase in his talk or in his defense about how not only does he develop these algorithms, but he really focuses on demonstrating them on actual systems and applications. One other thing I just want to really highlight about James, in addition to doing great research, is that he's actually been a great mentor to many UROPs. He's always been very thoughtful in terms of planning their research projects and meeting with them to provide guidance. And I see him often even late at night in the lab helping them debug. And in fact, some of his UROPs have actually gone on to receive awards, which is a great credit to James himself and his mentorship. So with that, I'm really excited for you guys to hear about all the exciting work he's been working on over the past few years in his PhD. So James, take it away.
Great. Thanks for the introduction, Vivian. Can everyone hear me okay? Okay, I see some thumbs up, so I'm going to assume it's good. So today I'm going to talk to you about my research. Like Vivian said, I work on time-of-flight cameras, and if you don't know what they are, I'll explain that shortly. I was advised by Vivian, and in addition, I received fabulous guidance and advice throughout the years from Professor Horn and Dr. Charles Matthey. So let's begin. So before we jump into time-of-flight cameras, let's take a step back and talk about depth sensors. And I'm sure many of you are aware that depth sensors enable many exciting emerging applications. One such application is a self-driving car, right? So you would hope that these devices, these applications have sensors so that they can navigate safely in the environment. You may have unlocked your phone with a depth sensor, right? And pretty soon, you'll be able to play games using them. And what these depth sensors allow you to do in this scenario is to interact with the environment realistically, and like I said before, safely navigate in the surrounding world. So, like I said, time-of-flight cameras are appealing depth sensors. And the way they work is they emit light into the scene and measure its round-trip travel time. So, if you're familiar with LiDAR, to distinguish here, we're flashing the light into the scene and capturing the entire reflection. So, these aren't necessarily foreign. If you played with a Microsoft Kinect V2, for instance, this is a time-of-flight camera. And with the emergence of many exciting new applications, there are also new depth sensors. Here's a recent one released by the company Sense Photonics aimed at automotive and industrial applications. Now, like I said before, the nice thing about these sensors is that they simply emit light, and by accumulating its reflection, estimate depth. So unlike LiDAR, which has to have a moving part, or like stereo cameras with a large baselines, you can make these sensors quite compact. And here I show that the sensors can be integrated into a smartphone. And given how these sensors measure depth, you can obtain dense depth measurements with minimal latency. Here I show a depth map, which is basically an image where the pixels represent the distance to different parts in the scene instead of the intensity, as you would expect in a regular image. And to summarize, these sensors are appealing because they have no moving parts and are fairly compact, so you could integrate them into different applications. And they obtain dense depth measurements with minimal latency. So if you're, say, a self-driving car, you can react to quick changes in the environment. What's the catch? Well, as you would expect, these sensors can be power hungry. They're active sensors, which means that they emit light, like I said, to measure depth. And the power they consume scales with the range. So for example, for a range up to 8 meters, you can find commercial time-of-flight cameras consuming up to 20 watts. For reference, for your mobile phone or your embedded gaming device, you want to keep the power appreciably under 1 watt. And as a result, for battery-powered devices, you're really going to cut down on the application time. And this is especially true if you need depth continuously. So imagine you're a robot interacting in an environment, or you're playing a game. You want to make the battery life last as long as possible. So this sensor, if it's running continuously, can really be a detriment to your battery life. And even if you're not power constrained and you run on wired devices, one issue might be the increased heat dissipation. This makes sense because you're emitting light, things will heat up. And one drawback of things heating up is that it affects the surrounding electronics and forces the addition of bulky heat sinks, right? Which kind of defeats the point of this compact sensor. So as the title of this talk implies, my goal is to lower the sensor power of the time-of-flight camera, right? But while doing this, I want to ensure that we still obtain accurate and dense depth maps. And as homage to the systems part of my research, I want to ensure that I can minimize the latency of our approaches. We want to efficiently estimate depth maps on low power processors. Why low power processors? One, they're ubiquitous. Most people have smartphones, and those processors are quite low power. The other thing is more from an engineering standpoint. There's no reason to develop algorithms to estimate new depth maps or to denoise them if the power of computation exceeds that of the depth sensor itself. So how are we going to do this, right? So what are the strategies we're going to take to lower the power of the time-of-flight camera? So our approaches fall into two strategies. The first strategy is to reduce the usage of the time-of-flight camera, all right? That's simple enough. And here we assume that we have RGB images collected in a separate sensor. RGB images can be efficiently collected because they rely on passive light, basically light in the ambient environment. And they're commonly collected for different purposes. So our goal is to reuse them. And as you can see in this figure, the RGB images are shown in the first row. In the bottom row, we want to estimate depth maps in time equals 1 and time equals 2. How are we going to do this? Well, I'm going to show you in this talk by presenting algorithms that use the data across consecutive frames to estimate the 3D motion in the scene, from which we can then obtain a new depth map without using the time-of-flight camera. And you can imagine we can do this sequentially. And by doing this, we can obtain dense and accurate depth measurements without using the time-of-flight camera. But let's just say you don't have this extra sensor. You don't have the room on your mobile phone, the extra room to put this sensor, and you just want to use the data from a time-of-flight camera. Well, what can you do? Well, the simple answer is just to reduce the light the time-of-flight camera emits. But there's no such thing as a free lunch. So for example, if you look at the bottom here in this depth map, we see that the depth map is locally smooth and the features of the chairs are pretty well preserved. Now compare this to a low power depth map that's considerably noisier and grainy, right? So how are we going to resolve this issue? So our goal in this case is to denoise the low power depth maps, to increase their accuracy by combining the data across frames. And in the same vein, we're going to use the infrared images that the time-of-flight camera collects alongside estimating depth to estimate the motion in the scene, to then combine the data across frames. And we can do this sequentially, thereby increasing the accuracy of the depth maps without increasing the amount of light we emit. Now, so our contribution, as you'll see in this talk, before I dive into this talk, like Vivian said, I really spent a lot of time thinking through my goals and how to balance the different aspects. So I'm looking to develop algorithms that balance the usage of the time-of-flight camera, the accuracy of the depth maps, and the latency of my approaches. So if we compare our approach to something that estimates depth strictly using monocular images, obviously the time-of-flight sensor power is low here, it's not being used. But this comes at the cost of reduced accuracy and high latency on these low power embedded devices, right? On the other extreme, we can just use the time-of-flight camera continuously like before. While they obtain accurate and dense depth maps with minimal latency, this comes at the cost of increased power consumption, right? And we'll see that our approaches lives somewhere in between these extremes. And by paying careful attention and designing the algorithms appropriately, what we can do is have the best of all the worlds. We can lower the sensor power and obtain accurate and dense depth maps with low latency on embedded processors and laptop computers. So what's the framework that we're going to use to evaluate our approach? How are we going to actually measure the sensor power, the accuracy, and the latency? So to present a common framework for the approaches we're going to present in this talk, I'm going to do this now. So for sensor power, I'm going to look at two proxies. In the case where we're using the time of flight camera less often, we're going to use the duty cycle. Basically, what's the percentage of frames where the time of flight camera is used? So obviously, a lower duty cycle means we're using the time of flight camera less often. We're using it infrequently. When we're using the sensor all the time, when we're always emitting light but reducing the amount that we emit, we're going to look at the normalized power. That's a fraction of light emitted compared to a regular depth map. Now, to quantify the accuracy of our approach, we're going to look at the mean relative error. And what from the name, which is intuitive, it penalizes a unit error more so up close than further away. And this is intuitive for applications that need to react in its immediate environment. Think self-driving cars. And finally, for latency, we're going to quantify the estimation frame rate on a low power embedded processor and the CPUs of a laptop computer, right? So like I said, we want to take advantage of the ubiquity of these devices. And also, I want to stress here that because we have this constraint, we want to do this efficiently on these low power processors that have also limited computational resources. It makes our problem quite challenging. And it's challenging because, as you'll see in this talk, the problem we're trying to solve is underdetermined. I'll explain what this means soon. We're trying to estimate 3D motion using 2D data. And from the latency standpoint, from the frame rate, we're going to require dense computation. We're going to need to estimate depth for every single pixel in an image. So for reference, a 640 by 480 image, that's over 300,000 pixels. And if I just cut off now, or if you leave, the main takeaways that I want you to have is that the way I overcome this is to assume that scenes contain rigid motions, and I'm going to use them to estimate and denoise depth maps, right? And this is an assumption made by many applications and an assumption observed by the many early pioneers of computer vision. But from an engineering standpoint, I like rigid motions because it turns out I can efficiently estimate them using sparse operations and linear least squares, which we'll see in this talk. Now with that, here are the publications that went into my thesis. In the interest of time, I'm going to talk about the following subset. So let's begin. Like I said, this talk is divided into two parts. In the first part, we're going to talk about how we can reduce the usage of a time-of-flight camera and estimate new depth maps instead. We're first going to consider the case of rigid scenes. What do I mean by a rigid scene? Well, here's an example. We're assuming that a robot or the user is moving in a static environment. Okay? But even in the age of social distancing, the world is not rigid. There are other components, other people walking, there are other things going on. And then we're going to show how the tools we develop in this section can be extended to handle dynamic scenes. And here we see that the character interacts independently from the moving world behind her. After this part, we're going to segue into how we can use the principles developed in the previous section to reduce the light the time-of-flight camera emits. And in particular, like the teaser slides I showed earlier, I'm going to show how we can adaptively control the amount of light the sensor emits. And then we're going to conclude with a summary of our contributions. So before I continue, are there any clarifying questions? Okay, so let's get started. So to estimate depth maps in rigid scenes, like we saw, our inputs are 2 consecutive images in a previously measured depth map. Our goal is to estimate the depth map in the current frame. We're going to assume, what I want you to notice is by looking at these images that there's not a lot of motion, right? And this is important, and we'll see how we use this observation later on, which leads us to think, well, if there's not a lot of motion, perhaps if we can estimate the pixel-wise motion between the images, we can update the previous depth map to obtain a new one, right? So many approaches in the literature leverage this idea, and they estimate the dense optical flow between the images to remap the pixels of the previous depth map. Now, like I said, what is this optical flow? So optical flow is the apparent pixel-wise motion. It's basically how the pixels move from frame to frame. So let's say we wanted to find the optical flow for this pixel right here. It's the corner of the monitor shown in red in the previous frame. We search in the current frame for its correspondence. And if we were to overlay these images and their red dots, we can draw the following arrow. Obviously, I've enlarged it for visualization. It's much smaller. And we can repeat this for the different pixels, right? And here I show them on the corner of this monitor and the keyboard. So using this information, what we can do is use the optical flow to move the pixels of the previous depth map, right? To remap them. But as you'll see in this presentation, computing dense and accurate optical flow is computationally expensive, especially on the platforms we consider, the computational platforms we consider. So what do we do instead? As I hinted in the beginning of the introduction of this presentation, we're instead going to estimate the rigid motion in the scene. And we're going to show how we can do this using sparse optical flow. So let's get started and use a simpler example. In this example, the M at MIT is moving. We have the two consecutive images and its previous depth map. So to use the image data to estimate changes in 3D depth, we're first going to have to describe our image formation model. Basically, how do points in 3D space get mapped into an image? And to do so, we're going to assume perspective projection. So how does perspective projection work? Well, here's the point cloud of the M, and this rhombus, this square right here, is an image plane that we want to map these 3D pixels onto. So what's needed in perspective projection? Well, we first need a center of projection, which is separated from the image sensor or plane by this principal distance. And to get an image, in this case, what you want to do is first connect all the points on the point cloud to the center of projection and take its intersection with the image plane. And we have the image as shown here. Using the same relationship, we can also do the reverse, meaning we have the depth map. We can get the 3D position of each of its pixels. And so we do this in the previous frame. We use the previous depth map to obtain the point cloud. Now we see that from the images that the M has moved. So we want to ask ourselves, how does the M move in 3D so that we can get this new image? So to consider this, instead of looking at every pixel in the M, let's look at this pixel, this red dot right here, right? We know in the next frame, it corresponds to this pixel. So what we want to ask now is, what does perspective projection tell us about how the red dot moved so that when we connect it to the center of projection, it is overlaid with the green dot? Well, if you were to follow that, we see that this red dot has to move to somewhere on this dotted line, right? Any point on that dotted line, when you connect it to the center of projection, will intersect at that green dot. But as you can see, this location is ambiguous. There are many possible positions it can move to. And this is the underdetermined nature of the problem I'm talking about. And we can see this mathematically as well. So this equation expresses what I just told you verbally and showed you using figures. I use this vector to represent the 3D coordinate in the previous depth map, which I, again, obtained using perspective projection. We want to estimate its 3D displacement due to rigid motion. And I highlight it in red because it's an unknown, which we want to estimate. And we're going to take its cross product with the following ray. This ray connects the center of projection to the green pixel, its correspondence in the current frame. And what this relationship says is that after the point has moved, it has to live on that dotted line. And again, from this equation, because cross product you can think of as a skew symmetric matrix with rank 2, you get 2 independent equations and 3 unknowns for each pixels. And so that's bad, right? This is underdetermined. We can't estimate it without any other restrictions. So the way we resolve this is to use the rigidity assumption. And because the time between frames is small, this allows us to approximate this quantity in red with the following, where omega, which is a vector in R3, can be thought of as the angular velocity, and t can be thought of as the translational velocity. And now we have 2 independent equations and 6 unknowns. But what's different is that these 6 unknowns are shared for every point in the point cloud, which means that with 3 pairs of correspondences, we can solve for the rigid motion. In practice, you want to use more than 3 to mitigate the effect of noise. But what I wanted to highlight here with this brief overview is that we can estimate the rigid motion using sparse correspondences, and in this case, linear least squares. And it's easy enough to extend this to estimate the rotation and translation matrix, but I won't go into the details of that here. So now that we've estimated the rigid motion, how do we obtain a new depth map? So the previous approaches, remember, use dense optical flow to remap the pixels of the previous depth map. Here, we're going to show how we use this estimated 3D motion to reproject. And there's a subtle difference here, and I'll explain why. So we first get the 3D position of each point, right? We know how to do this using perspective projection. We apply the rigid motion to these 3D points. So you apply the angular velocity and translational velocity, and then you map its updated depth to the image. And the difference here is because we're working in 3D space, we can account for changes in depth along the z-axis, whereas the techniques that simply copy or remap pixels do not. Okay, so now that I've briefly explained these fundamental blocks that we're going to use, let's see how we use it in an actual rigid scene. The inputs are the consecutive images in the previous depth map, and we're going to estimate the optical flow. As you would expect, there are many techniques to estimate optical flow. But because we're going to be judicious with our computational budget, we're going to use a lightweight heuristic. And in fact, we're going to use block matching to estimate the optical flow on a sparse grid. So how does block matching work? Suppose we want to find the optical flow for this pixel right here, shown in red. We first take a window around it, and we search in the next frame in the search window. But instead of searching exhaustively, meaning instead of doing an exhaustive comparison to every single position, we reduce the number of positions depending on the heuristic. So this is what I mean. So I would compare the red box to the box, this green box, this green box, this green box, and then I can continue, right? So now I've done 5 comparisons. And after I've done these 5 comparisons, I would say, well, the best matching point is there, and from that data, I can obtain the optical flow. Now, you'd say, well, James, you got lucky, right? And I did. But this is a conscious decision that I made to reduce the complexity of the algorithm. And I'm aware that sometimes you'll make mistakes. And because of that, I'm going to then estimate the rigid motion using a technique known as ransack. And basically, at a very high level, what ransack allows us to do is to mitigate the impact of the incorrect correspondences obtained by block matching or outliers. So here are the corresponding pixels identified with the block matching algorithm, right? And as you can see, what ransack allows us to do is to separate the good correspondences, the inliers, from the erroneous ones, the outliers. And then at the same time, also estimate the pose. So we use this technique so that we can mitigate the impact of so we can use the low complexity block matching algorithm, even though it can sometimes mess up. So when ransack succeeds, we reproject the depth map. But otherwise, when it fails, we use it as a signal to use the time of flight camera, right? So this allows us to adaptively use the sensor based on how we estimate the scene. So how does this algorithm perform in rigid environments? Well, we first evaluate our approach using RGBD datasets that are used to evaluate things from robot navigation to 3D reconstruction. Each frame contains an image and a depth map, and there are 640 by 480 resolution. And we're going to estimate the depth using the consecutive images and use the depth maps whenever the rigid motion cannot be estimated using RANSAC. And like I said before, we're going to evaluate using the framework that I established at the beginning. We're going to quantify the duty cycle. Lower is better. The mean relative error. Lower is better. And the estimation frame rate on the Odroid XU3 processor. So, the Odroid XU3, that's a mouthful, but basically it's the same CPU as the Samsung Galaxy S5, which was released in 2015. And obviously we want a high frame rate. And to make our lives a little bit harder, and you'll see why, we're only going to use the low power CPUs. But the reason for that will become apparent in a few slides. So the first question we can ask is, how low can we reduce the duty cycle? How low the usage of the time of flight camera while still maintaining a reasonably accurate depth map? And in this case, we choose a mean relative error of 1%. You can obviously change it depending on your application. So you see that with this work, we can reduce the duty cycle to 15%. We can across the different data sets, we obtain a mean relative error of 0.96%, and we obtain a frame rate of 30 frames per second, right? So this is considered real time. But could we have done better? We made the decision to use block matching, but there are obviously other techniques to estimate optical flow more accurately. So we can compare to a variant of our approach that computes this accurate sub-pixel optical flow. And when we do this, we see that the mean relative error does decrease. We would expect this. It's more accurate, so you can estimate the rigid motion more accurately, and from which you could reproject a better depth map. But this comes at the cost of the frame rate. The estimation frame rate drops by a factor of 2 on the low power cores of the Odroid XU3 board. And this kind of shows how we design our algorithms, gives you a flavor, right? We're trying to balance the accuracy of the depth maps with the estimation frame rate so that we can get the best of both worlds. What's the impact of using rigid motions? I made the claim earlier that estimating rigid motion is more efficient, therefore we should have a higher frame rate than using dense optical flow. And we should also be able to account for changes in depth. So we can compare our technique to Wang et al., which uses the dense optical flow to remap the pixels of the previous depth maps, exactly what we want to avoid. And here are the results. And as you can see, accounting for the changes in depth does give us better accuracy. And if you look at the frame rate on the Odroid XU3 board, we see that we can estimate significantly faster than this previous approach. And it's really, again, because the rigid motion can be estimated with sparse optical flow and linear least squares. So before I show you some cool videos, let's talk about system power. So I told you I made my life harder earlier by using the low power cores of the time of flight camera. So why do I do that? Well, I do that because I want to keep the power of computation low, so that if I use it in conjunction with a time of flight camera, I lower the overall system power. So in this table, I show the power for commercial time of flight cameras with a range of up to 3 meters. If you look at sensors out in the industry, you can get anywhere from 1 to 5 watts. And if we measure the power on this Odroid XU3 board using the low power CPUs, we see that the power is well under a watt. Given that we have a duty cycle of 15%, meaning we use the time of flight camera for 15% of the frames, we can compute the system power. And in the extreme case, we show that we can reduce the system power by up to 73%, right? So, and naturally this will scale for, if your time of flight camera consumes more power, but this kind of gives you gives you the motivation for why we want to reduce the complexity. It's so that we can run our algorithms efficiently on these low power processors. So with that, here's an example of our estimated depth maps. As you can see, it traces the measured depth, what's being measured. But what's more interesting is that these depth maps can actually be used in a real application. And here I'm going to show my work with Alan, who I mentored as a super Europe and now for his master's. And what these depth maps are used for in augmented reality is to properly orient 3D models, and they're also used to help localize the camera so that when you render a 3D object and you move, the dragon will remain fixed. So I want you to keep an eye on the dragon. So in the last panel, there's a dragon sitting on the keyboard in the panel labeled augmented reality. And as you'll see, as the camera pans, the dragon will remain fixed. So again, and this is running off of our depth maps, right? So in addition to like providing numerical evaluations, we show that our approaches actually work for real applications. So to summarize this section, we showed that we can estimate accurate and dense depth maps efficiently by reprojecting a previous one using the estimated rigid motion. We use this rigid motion to account for changes in depth, right? And this allows us to estimate more accurate depth maps. And it turns out that the rigid motion can be efficiently estimated using sparse block matching. And as a result, this runs in real time on a low power embedded processor. And it allows us to really lower the power of the time of flight camera, the system power for depth sensing rather, right? So before I move on, are there any questions? Because the building blocks I've introduced here will be used to both estimate depth in dynamic scenes and also denoise depth maps. Okay, I'm assuming no questions. So next, we're going to talk about the case of dynamic scenes.
You have one question.
Okay.
Thanks.
Yep.
Amr, do you want to ask it?
Yeah, so James, did you consider using an IMU or inertial measurements to guide your search in the rigid body motion?
So for the rigid motion case, I didn't use an IMU, but you could definitely imagine confusing the data from the pose estimation using the images with the IMU. Now, the nice thing about using the image-based technique is where we'll see in the dynamic scenes. With an IMU, you can get the ego motion estimation. So you can estimate the rigid motion of the scene, if you will. But with images, you can then extend our approach to handle independently moving rigid objects, which an IMU cannot capture. I will add, though, that even in the dynamic case, you could use an IMU to account for the camera motion and then so that you could reduce the computation and estimate the rigid motion of the other parts. I don't know if that answers your question. It was a lot, but.
Yep, thanks. Yeah, that's good.
Okay. Okay, cool. So dynamic scenes, right? So the inputs to our algorithm are the same.
One more question.
Okay, one more question.
Hey, hi, James. It's Chen.
Oh,
so,
hey, Chen.
So I saw that you use RANSEC to calculate the motion. So, but I know that RANSEC have a kind of observable failure rate. So what's the failure rate of RANSEC in your algorithm?
So right now, so for this algorithm, right, so I use the time of flight camera 15% of the time. And of that 15%, RANSEC will fail.
Okay.
Yeah.
Okay,
so
50%.
Yep. So now we move on to dynamic scenes, right? So the difference here, let me just replay the video, is that the character is moving independently from the background motion. But, from these two images we see in the setup diagram, what's interesting is if you just look at the apple and ignore everything else, so mask it out with your eyes, you'll see that the apple and hand kind of have its own rigid motion. And that rigid motion is independent from that of, say, the background or the torso of the character. So we can then assume that these scenes, even though they're dynamic, are locally rigid. And in fact, this is commonly assumed for many approaches in the literature. We're obviously not the first to realize this. And the way these approaches then estimate depth is they first segment the scene into rigid regions, and within each region, estimate the depth. Now, I bold segment because it's computationally expensive, and you're familiar with the field. It's not even possible to do accurately all the time, right? So, and in fact, many algorithms first require you to compute the dense optical flow before you can segment the flow field to obtain the rigid regions. So in this work, what we're going to do instead, we're going to cluster the rigid motions. And you know, whenever we say rigid motions, this should be a cue for you to say, sparse computation, right? And we're going to use them to estimate a new depth map. So here's the pipeline of our approach. Like before, we're going to use our inputs are consecutive images in a previously measured depth map. Now we're going to crank up the computation. We're going to estimate sparse. We're still going to estimate sparse optical flow, but we're going to use subpixel optical flow at corners. We want to make sure we get all the rigid motions in the scene. And to get these rigid motions, we're going to cluster them. So what do I mean by this? So this is the photo of in the previous frame, where the red dots represent the pixels where the corners are detected and the optical flow estimated. It's not dense. We don't have an optical flow for every single pixel. And then, like I said before, we're going to estimate the rigid motion using Ransack. And if you forget the details, what Ransack allows us to do is to separate, to not only estimate the rigid motions, but also obtain the inliers, the set of pixels that correspond to that rigid motion. So this is shown here in this diagram. What we can then do is to remove these pixels from further consideration and save its rigid motion and repeat this process iteratively. Now at this point, we've estimated a bunch of motions. We know some pixels move up, some pixels move left. What's left to do is to determine which pixels move up and which pixels move left. And the way we're going to do this is to compute the photometric error. I'm going to describe this process next. So we first take the previous image and depth map from the previous frame. We're going to use the rigid motion to reproject the image. Now, why do we do this? We know that if the if a group of pixels, say in this case, the apple and hand, move with this rigid motion, if we subtract its reprojection from the current image, the residual error, basically the pixel-wise difference, should be low for those pixels. And we can repeat this for each of the estimated rigid motions. So here's an example of this. So here we obtain this photometric error using one set of angular and translational velocity. And notice that the background intensity is really low. This would suggest that whatever rigid motion we used corresponds to the background. Here's another example. Notice that the rigid motion for the hand and apple is quite low, right? So here, this corresponds to those set of pixels. So we can repeat this for all of the different rigid motions to obtain a cost volumes. And for each pixel, we can simply assign the rigid motion that minimizes this photometric error. And when we do this, we get the following labeling, right? So here in the assigned rigid motion, each color represents the index of the rigid motion we assign to that pixel. So, and we do this again without doing any prior segmentation, right? You could argue we're segmenting in the process of estimating depth, but this is, as you'll see, lower complexity than the previous approaches. Now, once we do this, we can simply reproject everything like at the beginning, like we saw in the beginning. So that's pretty simple. Okay, so how does this algorithm perform? We're going to evaluate, again, using RGB data sets. These data sets are used to evaluate driving algorithms. So there's some scenes where a car is driving through an environment to indoor SLAM applications, SLAM being simultaneous localization and mapping, which is used in robotics. Unfortunately, they have different resolutions. So we're going to have to break up our analysis of the duty cycle and mean relative error from the frame rate. We're going to estimate depth using the images. and use the depth map in the data sets at regular intervals, right? So we're using the time of flight camera here in this scenario at regular intervals instead of tying it adaptively to ransack or anything. And we're going to look at the same metrics, but this time we're going to estimate the estimation frame rate on a laptop computer. It's just, we'll talk about future extensions of this work, but the computation here is definitely more than the rigid scenes case. So now we ask, how low can we reduce the duty cycle? How low can we reduce the usage of the time of flight camera while still maintaining a mean relative error of 1%? So as you can see here, that the duty cycle is 33%. So dynamic scenes are obviously more challenging, right? We're using the time of flight camera twice as much as before. And if you were to run this algorithm at the same duty cycle as the previous rigid approach, we see that the mean relative error goes up by 81%, right, for the same duty cycle. Now, what's the impact of using this rigid motion? Meaning, could we have done just as well if you were just to go back to our previous approach that uses dense optical flow to remap the pixels of the previous depth map, right? And in some sense, this is a nice approach. It's non-parametric. We're not making any assumptions about the motions in the scenes. We can probably expect the computation here will be higher anyways. So does accounting for changes in depth really help? And here are the results. So if we compare the results for the same duty cycle, we see that accounting for the changes in depth does increase the accuracy for both sets of duty cycles. Now, before I conclude the analysis in this section, I want to ask the following question. Do we need previous depth maps to begin with? Now, if you remember at the beginning of this presentation, I had that spectrum, if you will. One end were approaches that estimated depth strictly using RGB images. And of course, the drawback, as we'll see, is that the latency will definitely go up. But we're going to compare to one such approach that uses depth maps using just images, and it does so by breaking the scene into rigid regions, which I discussed at the beginning of this section. It's a much harder problem. And what you see and this is reflected in the mean relative error, right? The mean relative error increases to over 10%. So we can see in our approach, by balancing the usage of the sensor into how we obtain depth, we can increase accuracy, right? And I made a small observation at the very beginning of the rigid scenes part. And it's because between consecutive frames, not much has changed. And by using lightweight algorithms, we can really capture most of the information explained by the images. So this is not only apparent with the accuracy, but we can see by looking at the frame rates that our approach has a much higher frame rate than even the optical flow approach. And this is a testament to the fact that by clustering rigid motion and assigning them using the photometric error, which can be efficiently computed, we increase the frame rate and obtain accurate depth maps. So to conclude this section, I showed that we can obtain an accurate depth maps efficiently by clustering and assigning the rigid motions without having to do any prior segmentation. We can still estimate the rigid motions using sparse optical flow, and this increases the frame rate in which we obtain new depth maps. And by using this photometric error, we can accurately and efficiently assign them as well. And as a result, if we were to lower the time of flight camera by 85%, we can still obtain depth maps within 1.7% of the ground truth in up to real time, depending on the resolution. So before I move on, future works, of course. I'm finishing my PhD, by the way, so this is future directions as a result. So if you're familiar with optical flow, one thing to keep in mind is that the lack of texture can be a problem. So we need texture. We need to basically be able to localize corners to estimate accurate optical flow. In the rigid case, this is not so much a problem because we can just use the time of flight camera more often. Ransack will fail in most of the cases, and we'll use a sensor more often. But here, if there are many independently moving objects and they're small, we may not be able to discern the corners and estimate optical flow. So naturally, when we want to explore how the photometric error can be used as a confidence map, and if enough pixels have low confidence, to use that as a signal to turn the time-of-flight camera on. There's also missing depth. Regions, as you see, regions that were covered, that were obstructed but uncovered due to motion, do not have depth values. And we see this in this example. Here, as the character moves her hand up and we estimate the depth maps, we see that the depth in the background is not available. And this makes sense because we're simply reprojecting the last previous depth map in some sense. And when we don't have the depth behind something, when it's uncovered, we can't infill it with the current approach. So naturally, we're going to explore low-cost infilling methods to overcome this challenge. And finally, there's the issue of runtime, right? As the depth map increases in resolution, the estimation frame rate goes down. And we're also running this on a laptop computer, right? We may want to run this on a embedded processor so that we can have the same nice story, again, of lowering power. So one way to speed up this frame rate and potentially lower the power of compute is to explore how our approach can be accelerated using specialized hardware to exploit the parallelism that's built in. Notice that we can estimate the optical flow in parallel. We can also compute the photometric error in parallel as well. So now I'm concluded this section on reducing the usage of the time-of-flight camera. Before I move on, any questions? Okay, so at this point, we're going to consider again the case where we don't use the time-of-flight camera. We don't use any separate sensor to obtain RGB images. We're only using the data from the time-of-flight camera itself. And like I said before, a time-of-flight camera obtains a depth map and an infrared image. So how then can we lower the power, right? We still want depth at every time frame. Well, the simple solution that you don't need an MIT PhD for is to reduce the light the time-of-flight camera emits. But there's no such thing as a free lunch. And one drawback of this is that you lose range. The reflected light intensity cannot be discerned from the ambient light in the background. But what if you only care about the depth in the background? Well, when you do this, it increases the noise in your depth measurements. So when you measure depth, it's actually not a fixed measurement, but rather it's affected by stochastic variation. And we can actually measure the variance of this by assuming that this noise is shot noise, and we can show that the depth variance is inversely proportional to the reflected intensity. And so what does this mean? We can visualize how this looks. So this is real data collected from a time-of-flight camera, from ADI's time-of-flight camera. And here we're visualizing the point cloud obtained under regular power and then obtained with 10 times less power, right? So it's regular power, low power, 10x less light. And you probably even noticed this in the beginning of this talk. Here we show the infrared images and the depth maps again, and you'll notice that the low power depth maps are quite grainy. But I want you to observe something that's pretty interesting. If you look at the infrared images, they look more or less the same regardless of the underlying power. And if you zoom in, you see that the low power depth map, yes, is a bit grainy, but you can still see corners, you can still see the seams of the bed, which leads us to think, well, okay, maybe we can estimate optical flow, and then maybe we could estimate the rigid motion. And we do exactly that, right? We use the rigid motion to combine depth maps across frames. So why would you want to do that? Well, you can imagine a simple scheme where you infrequently obtain regular high-power depth maps and use them to denoise subsequent low-power ones. And before I go on, I want to stress that this is different from our previous setup in that the time-of-flight camera is always on, but less light is emitted, and our goal is to mitigate noise instead of estimating a new depth map. And we're only using the data from the time of flight camera again. So this is also a nice property of this work. So here's a pipeline of our approach. You know, you probably, if you remember the first pipeline, you're gonna say, well, that's really similar. And that's by design. And in the interest of time, I'm only gonna highlight the differences. The first difference is, again, we have an image and depth map in both frames, both the previous and current frames. We're then gonna estimate the optical flow, do the rigid motion, but instead of reprojecting the depth maps, we're gonna combine it with a low power one, right? We do this because we don't wanna throw any data away. But when RANSAC fails, we're gonna use that signal instead to obtain a high power depth map, right? To obtain a new high power depth map. That's the main differences. And how are we gonna evaluate our approach? Well, we collected a data using this time of flight camera, right? So this is, again, the dorm room of my collaborator, Alan Cheng, who I've mentored for the, like I said, for the Super Europe and MEng project. We're gonna add to, what we're gonna do to get like quantitative analysis is we're gonna synthetically add shot noise. So shot noise is the noise that affects these low power depth maps. So we can isolate it from other issues that affect time of flight cameras. I'm not trying to shove this under the rug. I'll talk about it again in future directions. So if you have any questions regarding that, please, I hope to address them soon. And then we're gonna look at the normalized power, because again, in this case, the time of flight camera is always on. We're gonna look at the mean relative error, and we're gonna look at the estimation frame rate on the Odroid XU3 board. Okay, so first let's compute the baseline results. If you remember back to the beginning again at that spectrum I presented, this is the other extreme where you're using the time of flight camera all the time. You can get reasonably accurate depth maps with low latency at the cost of power. Don't fixate too much on the absolute values of the mean relative error. We're gonna be interested in the comparison, you know, with a low power, our algorithms, so on and so forth, right? So when you lower the power, you know, you see the mean relative error increases, you know, fairly significantly. It goes from 2.6 to 8.8%. But we're still able to obtain depth maps at 30 frames per second. So one thing you could do is like, well, you kept saying that good high power depth maps are locally smooth. Why don't we just filter this low power depth maps? We don't even have to use any temporal data, right? So one common filter is to use a bilateral filter. And this is a filter that preserves edges. And if you apply it, you see that that at low power, the mean relative error doesn't really go down that much, right? They're unfortunately pretty ineffective. And at the same time, the estimation frame rate also decreases. And this is because to filter depth maps while preserving edges, you have to adapt the filter kernels based on its position in the image. So how does our approach perform? If you look at it, we see that we can reduce the mean relative error significantly, rather significantly, and still do it within 30 frames per second, right? So in this case, we lower the mean relative error by 64%. Now, you'll argue, well, James, you're not really being fair here. In your scheme, you're still obtaining high power depth maps at some point in time, and you're using it to enhance these low power depth maps. This is obvious when you look at the normalized power column. Because the low power depth map is a constant, 0.1, our approach uses 0.19 power. So we can just increase the power, right? Increase the amount of light incrementally to equalize it and look at the mean relative error. And when we do that, we see that the mean relative error is still high. And you can look into the thesis. We have an explanation for why, but very briefly, this is because at low power, shot noise is especially pronounced. The depth variance is inversely proportional to the reflected intensity. So at very low power regimes, the error can go quite high. So let's just visualize the impact. So we had enough numbers. This is real data processed with our algorithms, and we're gonna show you the point clouds. And here, we're following the same scheme. We're using a high power depth map to denoise a low power one that's collected with 1/10 of the amount of light. And again, this data was collected with ADI's time of flight camera. So what this suggests is by using our algorithms, you could potentially use it for a 3D reconstruction type of application. So to conclude, the simple insight we leverage here is the fact that we can estimate the rigid motion using the data from infrared images, regardless of their underlying power. We varied the amount of light to infrequently obtain regular power depth maps and use them to denoise subsequent low power ones. And by doing so, we reduced the mean relative error of the low power depth maps by 64% in real time on an embedded processor. So some future directions, if this were to be actually incorporated into a device. There's the issue of sensor calibration. So I didn't go into this, but when you change the amount of light the sensor emits, the temperature of the sensor will obviously change, which means that the lookup tables you have to query will also change. So we have to be careful in our algorithm to make sure to account for this fact to ensure that we can, obtain the right conversions and lookup tables to get accurate depth. There's also the issue of saturation. Objects that are close to the time of flight camera can actually, in some sense, blind the sensor. What do I mean by that? The reflected intensity can overload the pixel array, and therefore you won't have depth for those set of pixels. And that means that subsequent depth maps may not be able to be denoised. And other noise sources. To get a quantitative evaluation, I added shot noise. But we have to also think about other issues in time-of-flight cameras. One of them, chief amongst them, is multipath interference, and see how it affects this approach. So with that, I'm going to conclude my talk. But before I do, are there any questions for this section? Okay. So
one question.
One question, great.
Hi, James. It's still Shane.
Hi, Chen.
So my question is, when you lower the power of the time-of-flight sensor,
right.
So the correspondence you can find between the consecutive images the number will be roughly the same or less, but the signal-to-noise ratio or the variance will be larger, right? Signal-to-noise variance larger. So okay, it is very intuitive in that you can get worse estimation about the rigid motion. So, but however, I thought that, the Ransink method, based on the registration method based on Ransink, haven't fully utilized all the information between the images. So have you ever tried to use a correlation-based method, such as a Fourier mirroring transformation to estimate the motion? I think that may be more accurate. Utilize the full
correlation methods for like block matching. Is that what you mean?
Say Fourier mirroring transformation.
Can you type that into the chat, please? But so to answer your question, we do see this impact, right? Like, so if I'm understanding it correctly, you're trying to ask if I can find other ways to find correspondences, and you're suggesting I use correlation methods?
Yeah, correlation methods. Rather than correspondences, we use correlation method.
Correlation method being that when you do the search, you're doing like the normalized correlation as a cost function. Is that what you mean?
So the very basic, the very naive solution is that you just search the space, right? You just reverse transform the image and do the correlation between the two images until you find the transformation which matches the best. That's the most naive.
Well, yeah, we find the transformation where we're finding the displacement here. We're not finding any affine transformation. But continue.
Yeah. It can be displacement, but I suppose that the correlation methods can help you to smooth out the noise and give you better accuracy on the low input power.
Right. Yeah. So I didn't go into the details here, but I am using a normalized correlation, right? So one thing I think, if I'm understanding your question correctly, is that what you'll observe is that when you collect infrared images, you're going to have different intensities, right? Where there's more light, it's going to be brighter. Lower light, to one degree, you can do like an equalization. But another cost function you do when you search is to do to do normalized correlation to account for that and have filter weights in how you determine the cost functions. The point is, I guess what I want to stress is it's not so much what underlying comparison cost you do, but rather that it's sparse, right? By doing something that's sparse, you can reduce the computation and you're ultimately obtaining the same thing.
So in that case, the case is computation. How does the power for the computation compare with the power of the time-of-flight sensor?
So for the odor board, for instance, right? Like in the first section, I had that table that was the power was under a watt, and I don't know, you know, I don't know what the ADI sensor is, but if you look at the spec sheets of different time-of-flight cameras, you can see that they range, you know, at least a year ago from 1 to 5 watts. That obviously has changed, but the power of computation has also changed. It's also gone down.
Okay, so you are talking about that so right now, I suppose still the power consumption of the time-of-flight sensor takes the majority of the entire power, right?
Right.
Yeah, I mean, increase the computation complexity is not an issue for the perspective of power.
Well, it is, right? Because your latency goes down. Again, we're trying to balance everything. So you could imagine running like a whole like neural net structure for motion, but you're paying with the cost of latency. You're going to get depth way too delayed. And that means you can't react to changes in the environment.
Agree. Yeah, latency wise it is. Thank you. Yeah, finish my question.
Thanks, Chang. Yeah. Okay. So, you know, so Chang brought up all the points that I wanted to conclude with this thesis, which is very helpful. So I showed that by balancing the usage of the time-of-flight camera with computation, we can lower the power required to obtain accurate and dense depth maps, right? We never completely turn it off, but we recognize its importance because, like I said, we can update it slightly to account for the scene motion to still obtain accurate and dense depth maps. By exploiting this rigidity, we can use sparse optical flow and linear least squares to reduce the computation of our approaches, and in some cases, estimate dense depth maps in real time. And we also show this in not just in simulation, but on an actual embedded processor, and show that our depth maps can be used for real applications. So before I open it up for general questions, this thesis would not be possible without the following individuals. I want to thank my committee, you know, Vivian, Berthold, and Charles. They've been extremely helpful throughout this entire process. Vivian's my advisor, and she's provided excellent guidance and really forced me to think at a systems level, even though I'm inclined to think more algorithmically and mathematically, right? So I really feel like this was a very important part of my education. I've been very fortunate to have taken and TA'd for Berthold in his machine vision courses. And I think that provided the technical footing for me to apply these machine vision techniques to lower the power for depth sensing. And he's been, you know, I've enjoyed our technical conversations over the years. And, you know, I first met Charles when I interned at ADI, right? And it's been awesome, right? This is where ADI is where I first got my idea. Charles has been extremely supportive, and he's the liaison between our research project at MIT and the algorithms group at Analog Devices. And he's made everything seamless. He's been able to get me engineer time, sensors, and provide guidance on how the time-of-flight camera works. And with that, obviously, this project would not have been possible without Analog Devices. You know, I mean, you saw throughout the slides that I used the sensor from Analog Devices. The PicoSense sensor is also from Analog Devices. They generously provided me with that. So I want to thank them for providing the funding for this project and the technical support, right? And in particular, I want to thank the following individuals as well who've contributed to different parts of the ideas presented in this thesis. In particular, I want to thank Sefa, Nicola, Charles, Atulia, and Tao. They were really my advocates that got this project started and you know, to get the initial funding to do this work. And in fact, I got this idea at an internship at ADI. So this company has been tremendously helpful, and I thank them, you know, from the bottom of my heart for their funding and support. And I also want to thank the MIT faculty and staff. I want to thank, you know, I've been here, if you know, I've been at MIT since undergrad, so I've been here for 11 years now. And I've met many wonderful people that have made my education so wonderful. I want to thank our group admin, Janice. She resolves all the logistics in the lab, from ordering expensive FPGAs and embedded processors to making sure we're well caffeinated. I want to thank my academic advisor, Terry Orlando, who's been, there at crucial junctures of my PhD to, reassure me that things are normal and things will be okay. And that's been incredibly helpful. And, throughout this entire time, I've met excellent professors. For my MEng, I worked in clinical inference with Professor Thomas Helt and George Verghese, and they taught me a lot of it's funny because I used a model-based approach to solve that problem, and I use the same thing kind of here to solve this problem. And I also want to thank Professor Jim Hom for letting me take and TA's embedded FPGA class, and Professor Oppenheim for his first year seminar, which really, got me thinking about research in a different way. And, he also taught me that I'm not cut out for magic. He had a magic seminar, and I took that as well. And I'm glad I stuck with the PhD. So the PhD would not have been possible without the support of my friends. And, I'm very fortunate to be in a lab where everyone's incredibly supportive and nice. And without these individuals, I would not have survived the PhD. And I enjoy our late nights together. And I promise I'll be back so that I can take you out to Five Spices for the Friday lunch special. And outside of my group, I have a wonderful group of friends who've made this possible. In particular, I want to thank one special friend, my girlfriend, Hanviol, who's put up with me and supported me throughout this entire crazy process. And of course, none of this would be possible without the support of my family, in particular my mother, sister, who's here with us, and my grandparents. So with that, any questions?
I have a detailed technical question.
Yeah.
James, I very much enjoyed your presentation. In fact, it seems even clearer than your written thesis. I don't know how that can be, but anyway. I very much enjoyed seeing you progress through this. So, and I sent you, various comments and questions we already resolved in email. I'll just pick something else. So, when you reproject the old depth map,
yeah,
at a certain point you start to see gaps between regions. So there's sort of a texture on there. Mm-hmm. And I was just wondering, that I guess is an artifact of the fact that you're reprojecting from the old to the new, rather than going in the reverse direction, picking the coordinates in the new and figuring out where they would be in the old. And that way you would avoid those cracks where the grouting needs to go in. Yeah. And I don't know whether having those gaps is of any significance in further processing, whether it would cost more to do it that way around. So maybe you can address that.
Yeah, so, so those are two types of holes, right? So like you said, it's because I'm doing this forward projection, if you will. And you can infill them using something as simple as a median filter for the small epipolar curves in the rigid case, for instance. But what's more pressing in my view, why we don't want to do reverse warping, is the fact that you could potentially occlude regions that are uncovered, right? Sorry, you can incorrectly infill regions that are uncovered. So when you map pixels in the reverse warping, you're just copying, you update the depth map and you copy them, right? But that means no holes will appear. But sometimes you want those holes to appear because, due to motion, you've opened up some region. And just to be more on the conservative side, I just wanted to leave those holes in there.
Okay, sounds good.
I have a question.
Yeah.
So it's in the same vein actually, because when you're calculating the error, you're actually calculating in the imager. You're going across pixels and finding the pixels where you find a correspondence, and then you look at the error. But if you went to the point cloud and just looked at X, Y, Z, then you probably, it would be fair, I guess. I don't know. It might give a very similar answer, but then you really are looking around whether in the point cloud.
So if you're looking at the point cloud to do registration, is that what you mean?
Yeah, well, to estimate the accuracy of this method. At the end of the day, you're getting a set of points.
That's true. Yeah.
In 3D space, and wherever there aren't any points, you say, okay, well, then I have no information here.
Right. Yeah. That is a valid metric, right? So, you know, you can look at, for each point, you can find the closest point and then measure like that distance, you know, the average Euclidean distance in that sense. Yeah, that is valid. We use mean relative error, and in our publications, we use root mean squared error and mean absolute error, just because that's what's used in the literature for depth map estimation. But I think the bigger thing really is the fact that one metric is typically not enough, just because you're aggregating the entire performance of an algorithm to one number, even if you move to the point cloud space. So what I tried to do in this thesis was to use applications to the extent that I could to see if my techniques actually worked, right? But yeah, what you mentioned is very, very valid. We could evaluate things by looking at the point cloud distance, maybe use ICP to measure the relative pose, and then quantify the error in that.
All right, any other questions before we go to the close portion?
So I think you did some great work in lowering the duty cycle in order to save power. Another thought I had is maybe a different axis is being able to lower the resolution of the depth map. Maybe that has benefits in power, but also form factor.
Right.
What are your thoughts on that, like being able to use your techniques to achieve lower resolution?
For lower resolution depth maps, that makes the processing simpler. But I'm surprised. I've never thought of that angle. And if anything, I wanted to increase the resolution. And I was
just to clarify, I mean starting with a lower resolution and being able to generate a higher resolution depth.
Oh yes, the super resolution problem. Yeah, so that's the angle in which I've looked at before. So really, what I've showed you is a technique to align depth maps, right? So what you can do is, if you have enough, if you have temporal data, and you can estimate the pose between the depth maps, you can align them quite well, and then apply like multi-frame super resolution techniques to increase the details and resolution of the depth maps. Fortunately, I didn't have time to go through with that approach, but you could use the principles here to accelerate the alignment process and then run it with your favorite multi-frame super resolution technique.
Any other questions? All right, so if not, I think the committee is going to go into a breakout room to discuss, and we'll bring James in a bit. So Charles and Berthold, we're going to bring you into you'll be asked to go to some breakout room. So it's like a private room that we can all go in, and I'll pull James in after we discuss for a bit.